So welcome to lecture number 32 of the Statistical Thermodynamics for Engineers. In this particular class, now we are going to we started looking at the vibrational spectrum, and we know the fundamental vibrational frequency that is associated. Now we are going to look at what happens to and we also saw that this fundamental vibrational wavelength leads to the knowledge of the bond strength for a diatomic molecule. So, but however, we also know that if you are dealing with homonuclear diatomics, okay, because the oscillations, the vibrational transition leads to radial gradients in the electric dipole moment during the harmonic oscillation. So generation of such moments or such gradients are impossible for symmetric molecules, which is in this case the homonuclear diatomics, because they are symmetric and they offer no spectral signatures owing to the molecular vibration. Now we also note that WE is much greater than BE. Okay, so we might expect that the excessive energy accompanying vibrational motion, okay, would automatically lead to rotational excitation. Okay, rotational excitation. So if we now actually employ a spectrometer with a very high resolution, we see actually not one single line, but a multitude of lines when we are doing the spectroscopy. So let us look at one such spectrum. So let's say this. Okay, and if you look at it, it will resemble something like that. So this is in the wave number or centimeter inverse this way. Okay, this is the central, which is basically omega E. Now here you will see a kindred of lines. Here we will see another set of lines. Okay, so this is called the P branch. We'll come to that, what they are. This is called the R branch. And this is omega E. Okay, so if you employ a spectrometer with a very high resolution, a high grating, you will find that there is no one single fundamental line like the one here, but you see a kindred of lines, okay, as indicated by this particular figure. Okay, rather two groups of lines. So this is one group, this is the other group. Okay, on the both sides of the fundamental wave number. Okay, the group of lines at lower wave numbers. So these are group of lines, lower wave number, which means higher wavelength. They are called the P branch, while this, okay, which happens at higher wave number, but lower wavelengths. Okay, so this is called the R branch. It's called the P branch, and this is called the R branch. Okay, the tip between the two branches is still centered around the vibrational wavelength. However, simultaneous excitation of rotational motion eliminates this anticipated vibrational frequency in favor of the replacement signatures on both sides. Okay, so simultaneous excitation of the rotational motion eliminates this fundamental frequency. That's what we mean. Okay, so let us do something called Ro-vibrational spectroscopy, which is also called the Simplex model. Okay, so in the Simplex model, the vibrational and the rotational energies must be additive. Okay, so a diatomic molecule can actually never undergo vibrational motion without also undergoing rotational motion. So a diatomic molecule, okay, can actually never undergo, okay, vibrational motion, okay, without undergoing rotational motion. Okay, and the rotational and the vibrational energies must be additive, therefore producing the Ro-vibrational spectra. So the Ro-vibrational spectra is given as this RV, this RV. You have V prime, V double prime, omega E plus J prime into J prime plus 1 minus J double prime plus 1 into, okay. So this is like a conjoined a rigid rotor slash harmonic oscillator model. Okay. Again, the single prime and the double prime refers to the upper and lower vibrational levels respectively, and it is used even when used to identify the rotational quantum numbers within each vibrational band. So for this simplex model, okay, the selection rules are still the same. Okay, still the same. Okay, so we obtain two separate cases corresponding to delta J plus minus 1, whether for absorption or for emission. So for clarity, okay, we can draw a diagram like this. So let's put the vibrational in right. So J double prime equal to 0, J double prime equal to 2, J double prime equal to 3. Okay. And then of course, okay, so this is J prime equal to 3, J prime equal to 2, J prime equal to 0. Okay, and this is V1. Okay, so this is a typical thing that you have. So the allowable things, if I put it properly, J2, J3, okay, J1 to J2 allowed. Of course, J0, J1 is also allowed. Okay, so and then if we put a demarcation, so this is actually the B branch. We'll see in a nutshell. So J double prime equal to 0, 2, 1. This is one possibility. Then other possibility, of course, is the third possibility. So this is how a typical Ro-vibrational spectrum would actually look like. Okay, so P branch refers to the case for which J double prime. So P branch really refers to the case where J prime is equal to J double prime minus 1, where R branch refers to the case where J prime equal to J double prime plus 1. Okay, plus 1. Okay. So these are the two corresponding spectral lines. Okay, so using this particular situation, okay, so the wave number for the P branch is omega e minus 2be j double prime equal to 1, 2, 3, da da da. Okay. Then of course you have the R branch, which is omega e plus 2be j double prime plus 1. This is utilizing the substitutions, and j double prime is equal to 0, 1, 2, da, da, da. So the spectral line spacing, spacing for both branches is delta P equal to delta R to E. Okay, so we can see that therefore the P branch produces a series of equidistant, Ro-vibrational bands, Ro-vibrational lines for, frequency less than omega e, where R branch, okay, produces a series of equidistant Ro-vibrational lines for greater than omega. Okay, this is what we suggested in the figure. If you look at this particular figure, this is what was suggested there, right? Okay, so we also note that again the fundamental pure vibrational frequency was missing because of the addition and subtraction of the rotational energy with respect to omega e. We have subtraction or addition of rotational energy. So so you can see that the spectrum, so there is a subtractive and then there is an additive for the two lines. Okay, so we can see right here, therefore, that the R branch and the P branch, they produces lines which are on the two sides of the fundamental frequency. Furthermore, because Ro-vibrational spectroscopy encompasses both vibrational and rotational motion, if we just do a least square fit of the spectrum, which we saw in figure 7.2 in the book, or the spectrum that we showed over here, okay, the P branch and the R branch of the spectrum, okay, so they would actually give us both the bond strength and the bond length. So if we determine BE and WE, we can calculate both the bond length and bond strength. Okay, we can calculate both the bond length and the bond strength. From a more practical perspective, when discussing a particular Ro-vibrational line, we must be able to describe it in an unequivocal fashion. As a result of that, we have developed this rigorous notation. Rigorous notation is B prime J double prime B equal to P. Okay. B is equal to P for a line in P branch, where B is equal to R in R branch. Okay. So if we say it is P25, let's say, for example, it designates, what does it do? It designates a transition, okay, from P prime equal to 2 J prime equal to 4 to V double prime equal to 1, J double prime equal to 5, or vice versa. Okay. Similarly, if we write R1, 5, this designates a transition. Okay, from equal to 1, J prime equal to 6, to V double prime equal to 0, J double prime equal to 5, or vice versa. Okay, so this is what a P line should look like, a sample. This is what an R line should look like. So this is more for a rigorous notation, okay, of the Ro-vibrational spectroscopy that we see over here. Okay, so let's look at a simple spectrum like this. Okay, so also there in the book, something like this. It's like crudely drawn. It's also given in the book. These are very sharp lines actually. Okay, the little bit of a width of the lines we will state later why they are so. This is the P branch, the R branch designates, V equal to 0 to 1 transition, okay, for gaseous HBr. Okay. So this is the P branch, this is the R branch, and this is where the fundamental will kind of lie. Okay. So these are on the both sides of the spectrum. Okay. So the only lacunae here is that the Simplex model understates the inherent complexity of combined rotational and vibrational motion. So if you look at that, at this particular infrared spectrum, which is figure 7.4 in the book, okay, you will find that there is no, consistent with the Simplex model, there is no pure vibrational line. Okay, the variations in line intensity again reflect analogous differences in rotational population. Okay. However, in comparison, if you look at the results, the spacing between the lines drops as we move within the P branch closer to the fundamental frequency or fundamental wave number, and this spacing rises in the R branch as the frequency approaches the fundamental frequency. So its Simplex model cannot really reproduce the X because the lines are supposed to be equidistant. So it cannot really reproduce the actual positions for the various transitions in the Ro-vibrational spectrum. So this general result underscores the limitation of this combined rigid rotor and harmonic oscillator model. So given this outlook, we need a more realistic model for the combined vibrational and rotational motions of a diatomic molecule. So for if the HBr spectrum, so just to formally write, spectrum indicates that okay, the spacing, and this is also figure 7.4 in the book, spacing between consecutive spectral lines, okay, within P branch drops as we approach, the frequency approaches the fundamental. Similarly, within R branch, this spacing rises as this approaches. Okay, so the Simplex model cannot reproduce to produce the spectrum, the actual positions, okay, for various transitions, okay, in the Ro-vibrational, spectrum, HBR. Okay, so this results therefore states that the combined rigid rotor and harmonic oscillator model is not a good example. Okay, given this outlook, we need a more realistic model. Essentially, that's what it is, right? So that is what is needed over here. Okay, so we need what we call a complex model, okay, for combined rotation and vibration. Need a more complex model. But before doing that, you can see the example in the book that where it says that the Raman spectrum of a diatomic molecule can be investigated by excitation with a laser beam. So the spectrum results from Ro-vibrational modulation of the scattered laser intensity to produce the side bands, which is basically the called around the laser frequency. Okay, and the Stokes component. Okay, we'll see what Stokes component is, but you can look at this example and you can apply the selection rules and you can work out. So this will give us a good idea. So we are not covering this in this particular lecture, but you can take a look at it. Okay, which is example number 7.1 in the book, chapter 7, basically. So, but let us just do a little bit of a discussion on the complex model. The simplex model assumes complete separation of vibrational and rotational energy modes. Complete separation. So the vibration is modeled as a harmonic oscillator, rotation is modeled as a rigid rotor. But we recognize, of course, through the HBR spectrum that the line spacing which was supposed to be equidistant are not. So their distance actually changes closer to the fundamental wave number. So this model is therefore too simplistic. We also saw that the harmonic oscillator was a good approximation of the Morse potential only at lower vibrational energies, right, towards the well. So as we go on to higher vibrational energies, because this well is for a particular electronic level, so within that well, as we go higher and higher, so if you look at it, so it is only valid for this lower part, this part, but the higher parts, okay, it is not a good approximation. This is the Morse potential, if you recall. Okay, and this is where the harmonic oscillator did a good job, supposedly good job. So this was the harmonic oscillator. So the harmonic oscillator in itself did a good job only in the lower part of the spectrum. It did a very poor job at the upper part, right, with the higher vibrational energies. Okay, so secondly, by imagining the diatomic molecule as two masses linked with a spring, we also realize that rotation will also lead to the stretching of this spring. So you will stretch the spring also. So this therefore makes a rigid rotor model virtually impossible. Thirdly, carrying this further, that enhanced vibration will also expand the mean bond length, okay, thus affecting the moment of inertia that is required for rotation. So in other words, there is a coupling between the vibration and the rotational energy levels. So what are the three things? Let us write it down quickly. One is basically the harmonic oscillator. Okay, only works for lower vibrational energies, energy levels. Okay. Second is rotation leads to stretching. So rigid rotor assumption is not good. Okay, and the third point, which is one of the biggest point, is that enhanced vibration, okay, expands the bond length, which further affects the moment of inertia. Affects the moment of inertia. Okay. So there is coupling between rotation and vibration, which is what we need to address. There's inevitable coupling between rotation and vibration, which is exactly what we need to clarify in the next lecture. Thank you.